And only if we have the variability of the wind stress over the ocean, in that case, we will have the vertical velocity, positive or negative, toward downward or upward. What that means? That means that the Eggman pumping is the process the process which creates the vertical velocity, which changes the height of the water column. Because the water column becomes higher, and then means more straight, or it will be shallower and will have the larger radius, the larger horizontal dimensions, which is this thing here. You can see this is, if you have the westerlies and easterlies down there. Westerlies are in the mid latitude, and trade winds are in subtropical areas. So here you have the spatial variability of the wind. Here you have the wind coming toward you, and here the trade winds are going into this screen. So due to this distribution of the prevailing wind or in the atmosphere over the ocean, the curl of the wind stress, so that means that the gradient of the wind speed between this area here and this area here, there, is non-zero. Being non-zero means that we have this right-hand side of the equation, we have non-zero forcing. So what is happening is that in this area here between westerlies and easterlies, the vertical velocity in the Eggman layer, you can see this Eggman layer. You remember that last time we were talking about it, essentially about two types of the layers in the ocean, or three layers in the ocean. One is the surface Eggman layer, which is this thing here, which is around 1,000 meters deep, or between around 400 meters. And then,
excuse me if I interrupt, but I don't know if it's only a problem of mine, but I'm stuck at the first slide.
Excuse me, I didn't understand. What did you say?
I'm stuck at the first slide.
Oh, now what you see now? You are always stuck at the first, huh?
Yeah, wind-driven circulation, the circulation of the ocean.
No, I changed the PowerPoint. You don't see Eggman pumping in the ocean slide?
No.
No. It's just the first page.
Now you don't see it?
Yes, it's only the first slide, wind-driven circulation.
Ah, it's always there?
Yes.
Yes.
Okay, let me. The best thing would be that I stop I stop sharing, and then I will restart the sharing of the screen. And let me see where I should find the. Now, what you see? Do you see anything?
Eggman pumping in the ocean and the two formulas.
Perfect. That's what I want.
Okay. Thank you.
Okay, so let's sorry for that. So let's go back. This equation here, which is the equation of the Eggman pumping, you remember we were discussing this last lecture, essentially shows that if there is the horizontal variability of the wind, which is the curl of the wind stress, so that means dx of the y component of the wind minus ddy of the x component of the wind, is different than 0, in that case we have the vertical velocity. The vertical velocity associated with the wind at the surface is due to the horizontal spatial variability of the wind field. So, and that's a very important aspect of the influence of the wind, of the influence of the steady wind. You have to always to take into consideration that we are talking about the Eggman. Eggman means the steady solution. Eggman solutions are a steady solution, no time dependence in it. So, how this looks like in the atmosphere, in the ocean, and in the atmosphere. In the atmosphere, we have trade winds in the subtropical areas, and we have the westerlies in westerlies in mid-latitude areas. And so that means that in the wind field you have the spatial variability. There are differences in the zonal component of the wind. So this means that due to this variability of the zonal component of the wind, there is the vertical velocity which appears essentially in the Eggman layer. Because the Eggman layer is associated to the Eggman solution, is associated to the Eggman pumping. You remember this figure also shows you the general scheme of the vertical structure of the ocean as far as solutions are concerned. In the surface layer, we have the Eggman layer, where the influence of the wind is important, where the Eggman solution is valid. Then we have what we call the geostrophic interior. Geostrophic interior is the part of the water column where there is a balance, there is the geostrophic balance as a good approximation of the flow. And finally, which is not shown here, is the bottom boundary layer or bottom Eggman layer, which is the third layer of the world ocean. Since we are talking now mainly on the Eggman layer and the geostrophic interior, we won't be talking too much about the bottom Eggman layer. So in this Eggman layer, where the Eggman solution, which means where the vertical velocity is associated to the spatial variability of the Winstress Curl, here the thing is that we have the Eggman transport here at the mid-latitude there, at the subtropical area, we have the Eggman transport northward. In the mid-latitude areas, we have equatorward Eggman transport. So here in this area here, we have the convergence. What means the convergence? The convergence means that we create the vertical velocity, downward vertical velocity at the bottom of the Eggman layer. So the water column, which is here, this high, this is it. This is the height of the water column going from the surface to from the bottom of the Eggman layer to the bottom of the ocean. If you pump the water in it, the water column stretches, becomes deeper. By becoming deeper, it, as we have seen before, it starts to rotate more faster, and therefore it gains the relative vorticity. But in order to preserve the potential vorticity for the constant depth, this water column has to move southward, has to move southward in order to preserve the potential vorticity. Because you remember the potential vorticity is the relative vorticity plus plus the planetary vorticity. This has to be constant. In order to be constant, this, since you are increasing the relative vorticity by stretching the water column will move by inertia, will move equatorward. So this is so this kind of the forcing creates the southward movement of the water column, or the movement of the water column in the equatorward direction. What is also important that the water column is stretching, and due to this stretching, it moves south. So that's the thing what we have to consider. And let's now go to this lecture what I told you. No, that's not. Here it is. And now I will. Can you see it now? Wind-driven circulation.
No, Professor.
You don't see it?
No, we see the Taylor-Prudman theorem.
Oh, okay, so let's go back. So I have to do again the same operation. I have to stop, to quit with sharing, and I will try to share the screen again, and now it's okay. Yeah, very good. Okay, so now we will be by giving you this this flavor of how the wind is influencing the water column in a specific place, in a specific situation where we have the spatial variability of the wind. We can talk about the wind-driven gyres and other wind-driven circulations. We will go down then on a description from observations. We'll be talking about the dynamics of wind-driven circulation, which we already mentioned about. Eggman Transport will be mentioned about, but this we will repeat it here because this is where the vertical transport influences. We will be talking about the Schroeder balance. Western boundary current will try to explain the western boundary current, why there is this strong asymmetry between east and west coast of the ocean. Certainly, all this is based on the observations, and so we will be addressing the observed wind curl and Schroeder transport in order to see to what extent this kind of solution are a good approximation of whatever is happening in the ocean. The heat transport is something which is on one hand we have a heat transport due to the thermal and saline differences between north and south, between equator and the polar areas. So this is the total heat transport, but we can also do the estimate of transport by wind-driven subtropical gyres. So separate the wind-driven heat transport from the total transport of simply due to the horizontal gradient of heat content. So ocean circulation, general circulation of the ocean is driven or forced by the wind stress, as we have mentioned this before, by buoyancy changes, but that means by the differences in sea surface in temperature and salinity. So we have the air-sea land ice fluxes. So we have the air-sea fluxes of heat. We have land-sea fluxes of heat, and we have also the diffusion. Diffusion is a molecular or turbulent diffusion, mainly turbulent diffusion, because turbulence is much stronger process than a molecular. So, but the diffusion is a slow process associated with turbulence in the water column. So, but this turbulence then, on the other hand, on its turn depends on the wind inputs and internal, into internal waves, and the buoyancy input that cause very small overturns in the surface layer. What that means, diffusion by buoyancy input. If you cool the surface water, what I have been mentioning before, then in the part where I was talking about the dense water formation, if you have a cooling of the surface water, this creates the vertical instability, the surface layer, the surface low water being of slightly lower density than the deeper water, which then causes the overturns, the vertical mixing in the surface mixed layer. This is why, if you remember, I showed you the vertical distribution of temperature, and you can see, you have seen that during the winter or during the autumn, you have the surface mixed layer due to these overturning of the surface mixed layer due to the buoyancy input, due to the input of or due to the loss of heat in the surface layer. Then we have the internal tidal braking against the topography, because if you have the tides coming and they are coming into the topography, into some deformation on the bottom, it breaks and then creates the diffusion. And then finally we have a cascade of energy into smaller scales from unstable current. If you have the current, which, as I told you before, the currents are not really rivers. They are unstable because you have the gyres which are formed along these currents. They become unstable because there are formation gyres, and then this energy from the current cascades into smaller scale from this unstable current. So, but that's the diffusion. But in this lecture, as it says here, the wind-driven upper ocean circulation and the heat transport associated with the changes in temperature along its pathway will be considered. So here we won't be talking too much about the diffusion, but we'll consider the wind-driven upper ocean circulation and the heat transport associated with the changes in temperature due to the ERC heat fluxes. These ERC heat fluxes, as I mentioned before, are something which creates the differences in temperature between polar and equatorial areas. So you have the mechanical forcing and thermohaline forcing, the forcing due to the differences in either temperature or salinity. Wind-driven circulation, and this is that's the figure I already showed you a few times. We showed the surface circulation in the world ocean, which is, if you look with a little bit of imagination, you can see that they are very similar to different oceans. This is what is important is the asymmetry between the western and eastern coast of the ocean. Western coast of the ocean are characterized by the stronger poleward flow with respect to the equatorial flow at the eastern part of the ocean. And the same thing, if you look at the Southern Ocean, you can see the same thing. Except that it looks like a mirror image of what is happening in a northern ocean. So that's how the general circulation, surface circulation of the world ocean looks like. And this is something which is the wind-driven circulation. Wind-driven circulation is a part of this general circulation. What you can see here. because the general circulation, as we are talking many times, is also driven by the differences in temperature and salinity between polar and equatorial areas. So the superposition of these two types of the circulation gives the total pattern of the world surface world ocean circulation, and so that's how it looks like. And here you can see all the Pacific equatorial current. You can see also the Antarctic circumpolar current, which is a very strong current, which is to a large extent driven by the wind. And here is the surface velocity streamlines. So this is complete velocity, including geostrophic and Eggman, based on surface drifters. So here we are supposed to deal with the entire world ocean circulation. The world ocean circulation, which is not only wind driven, but it's the whole world ocean circulation, independently what is the cause of this circulation, whether it's the thermohaline, geostrophic, or the Eggman-based circulation. And here is again that you can see that they are very similar to the previous figure. Again, this asymmetry between the eastern and western part of the world ocean, the circumpolar Antarctic current, the equatorial current, and so everything is really here present. And and this surface height is the same thing what I already showed you. This was obtained in centimeters, by assumption of geostrophy. What that means? Surface height in centimeters based on assumption of geostrophy. That means that we have had the measurements of the surface current somehow. Then what we did from the geostrophic balance, we reconstruct the sea surface pattern. So you have the equation, the equation of motion where you have the geostrophic, balance. You have on the left-hand side you have the Coriolis force, which contains the velocity. On the right-hand side you have the sea surface gradient. And if you have the velocity field, the surface velocity field obtains to somehow, you can calculate the surface height, because you have Fv is equal dx, and so V is equal G. We have V is equal G dV dx divided by F. Therefore, in that case, we simply looking from the dH dx is equal G Fv over G. So in that case, we simply, by having the velocity, we reconstruct the sea surface height in centimeters. This is the inverse process with respect to what we have done, what we do by having the surface height. If we have a surface height, which is the recent result from 1992 up to now from the satellite measurements, there we have the sea surface height distribution over the world ocean, and then we reconstruct the sea surface current. And here, before there was before the era of the satellite measurements of sea surface satellite measurements, the process was inversed. We threw away thousands of drifters into the sea. We measured with a rather large resolution the sea surface current, And from that, we reconstruct the sea surface height. This sea surface height obtained here from currents are very similar to what is obtained later on from satellites. Again, here there is western boundary intensification of the circulation and the stronger gradient of the sea surface on the western boundaries of the ocean, or a relatively weak sea surface gradient at the eastern part of the ocean. So this is that's the surface, and this is what is the vertical distribution, vertical structure of these gyres. Vertical structure of these gyres is this thing here. Here is the vertical gyres from the surface layer, and you can see this is the pattern what we have seen here. If you go deeper, they remain western intensified but they shrink toward poles. And if you go even deeper, these vertical gyres become more and more shrunk. So the surface subtropical or mid-latitude gyres decreases in its strength, in its extension, spatial extension, by going deeper and deeper. Except that you can see that the Antarctic circumpolar current remains weakly, changes relatively weakly with depth. So this now we already discussed the Eggman transport. This is the vertical distribution of the vectors, and the Eggman transport, which is 90 degrees to the right-hand side with respect to the wind, or around 45 degrees with respect to the surface current. So wind-driven circulation is due to this spatial variability of the wind, can have these divergence or convergence due to the Eggman transport. But as we were just mentioning last time, we can have the boundary, the divergence or convergence, we can have it next to the coast. If we have the wind blowing in such a way, leaving the coast on its right, for example, leaving the coast on its right, what is happening? The Eggman transport is toward the coast. Okay, so the coast is like a vertical wall. This vertical wall blocks the water, so you have the increase of the sea level near the coast. You have the convergence in the coastal area, and then consequently you have the vertical velocity downward. So this is what we call downwelling, and vice versa. If at the northern hemisphere you have the wind blowing, leaving the coast on its left, okay, in that case the Eggman transport is from the coast toward the open sea in the surface layer, in the Eggman layer. I always talking about the Eggman layer. When we talk about the wind influence, we always talk about the Eggman layer. So in the surface we have the Eggman transport from the coast toward the open sea. What that means? That means that we're losing the water in the coastal area, so we have the sea level going down. And so we have the divergence in the coastal area and loss of the water, which is partly compensated by the water in deeper layer below the Eggman layer flowing toward the coast. So we have this kind of closed, semi-closed circulation in the surface layer. The Eggman transport drives the water from the coast toward the open sea, while in the deeper layer below the Eggman layer we have the onshore transport, and in the coastal area we have the we have the upward vertical velocity. So due to this thing here, what is the structure of the isopycnal? These are the isopycnals. This is the vertical transect, and far from the coast, the isopycnal are horizontal. Okay. When you approach to the coast, what is happening? Since this is the vertical velocity toward up, there is a transport of the colder water, of the denser water into the surface layer, and therefore the isopycnals are sloped up in the coastal area. Okay. So what you see is that, how do you recognize that the upwelling area? The upwelling area you simply recognize by seeing the water, the presence of water from deeper areas. Okay, so the presence of water from the deeper areas in the coastal area is the sign of the water transport, of the Eggman transport, due to the wind influence, which leaves the coast on its left. Deeper water in the ocean. How do you recognize the presence of this deeper water in the ocean? You recognize it by temperature, because usually it's always the temperature in a deeper layer water. Deeper layer water is colder than the surface water. Therefore, the upwelling area is recognized by the cold water, by the presence of cold water in the coastal area. This is one of the main indicators. One of the main indicators of the presence of the upwelling, of the coastal upwelling. Here is the what I already told you before. Is the equatorial upwelling, which is due to the trade winds along the equator, where due to the changes of the Coriolis force direction, there is the Eggman layer transport divergence north with respect to the south, because here in the northern part, north of the equator, the Eggman transport is to the right-hand side of the wind. That means from the equator toward the poles. The same thing or similar is in the southern hemisphere, south of the equator. The Eggman transport is to the left-hand side of the wind direction, and therefore the Eggman transport is from the equator again to toward poles. So as a consequence of that, along the equator, you have the divergence, and you have the upwelling. You have exactly the same thing as it happens in the coastal area. So the upwelling is due or to the presence of the coast, or to the changes of the orientation of the Coriolis force passing from the northern to the southern hemisphere, passing from one side of the equator to the other side of the equator. But so this is how it looks like. The cross section, you can see the equator, and there is a Eggman transport to the southern hemisphere in one direction, northern hemisphere in the other direction, and the wind is into the screen. And here you have the upwelling. Again, the upwelling is seen as a bump in the isopycnals, or in the upward motion of the constant of the isopycnals. But there is another phenomenon which is associated to this. This is the sea surface. You can see that this sea surface shows the valley. Shows the valley. Why it shows the valley? Because there is the loss of water volume from the equator in the area of the equator, because you have a divergence. Having the divergence Yes, partly this divergence is compensated by the flow toward the equator in the below the Eggman layer, but not completely. Some water is lost anyhow. So this can be seen in terms of the valley in the sea surface. Obviously, the sea surface valley is not on the order of meters or hundreds of meters. The valley is on the order of a centimeter. So you have the gradient, the sea surface gradient on the order of a centimeter, while the gradient in the thermocline position is on the order of hundreds of meters. So this is a huge difference in the slope of the thermocline with respect to the slope of the sea surface. Exactly the same thing is happening in the coastal upwelling. When you have the divergence, or when you have the water loss in the coastal area, the sea level is sloped down. At the same time, as you can see here, the isopycnus or picked thermocline is sloped up. So these are similar equivalent situation for the for either upwelling, coastal upwelling, or the equatorial upwelling. Now let's see the Eggman upwelling or downwelling and the open ocean. Oops, what is happening? Sorry, there's something which every now and then comes to my computer, and I don't know how to get out of this. Sorry. No, I have to. Sorry. I have to move this thing. Okay, here it is. So this is the wind-driven circulation, Eggman upwelling or downwelling in the open ocean. As I mentioned a little last lecture, this downwelling or upwelling can appear due to simply and as we see also from the Eggman pumping relationship, that the divergence or convergence, downwelling or upwelling, can appear simply due to the Winstress Curl. Okay, and so let's see a very simple example which is associated to the zonal distribution of the wind field. Here is the if you look at this as a maximum zonal field wind in a certain latitude, and it goes down equatorward and goes down poleward. So what you see here is here in this part here, the Eggman curve, the wind curve is negative. Here is the wind curve is negative, okay? Because you have the reduction of the velocity starting from here to there, and here you have the wind curve is positive. So we have, if the wind curve is positive, we have the upwelling, the Eggman divergence, and we have the suction. This sucks the deeper layer water into the surface, into the surface water. So you have the kind of the similar situation what you had here. What you had here at the equator upwelling. In the southern part of this maximum of the zonal wind, you have the negative Winstress Curl, and you have the pumping of the water downward. So you have a downwelling here and upwelling there. Because the Winstress curl is non-zero. If it were a constant all over the area, the Winstress curl would be zero, and there would not be the vertical velocity would be zero either also. So when the curl is positive, there is an upwelling in the northern hemisphere. When the curl is negative, there is a downwelling out of the Eggman layer. You always have to consider that we are talking about upwelling and downwelling, which are happening in the Eggman layer because there the wind influence is felt. So, so that means that if we know the spatial distribution of the Winstress curl, we will be able to reconstruct the upwelling, downwelling areas of the ocean, and not only that, we would be able to reconstruct the water movement which are generated by this Winstress curl, because from the potential vorticity conservation, we know that if we create the negative relative vorticity, the water column has to move southward and vice versa. So not only that we create upwelling or downwelling locally, but we are also creating the horizontal movement of the water column. So the double action on the wind. On one hand, it changes the vertical structure of the water column on one hand. On the other hand, it generates the horizontal current. Here, let's see the Winstress curl from satellite, because we are able to measure the wind stress or wind velocity directly from satellite, which has a very high spatial resolution, similar as sea level. And you can see that this is the negative Winstress curl is in the part where there is the subtropical gyre. So you have here a downwelling. The positive Winstress curl is in mid-latitude areas, mid-latitude polar areas, where you have the upwelling. And then you have the equator. You can see the equator. The equator is clearly seen from the equatorial upwelling. You can see this is the equatorial upwelling, which is created due to this to the Winstress curl, which is positive in the equatorial areas. So this shows you very nicely how the Winstress curl changes at the Earth, simply at the ocean. But obviously, there are a lot of fine-scale structures in the Winstress curl, but which are not due to the planetary distribution of the Winstress curl. It's due to the presence of the orography. Here is Cuba and Mexican Gulf islands, and you can see that there are some dark blue areas where the Winstress curl is negative. The similar thing is here to the other side of the Mexico. So apart from these large-scale structures, which are subtropical gyre, mid-latitude gyre, we do see here an equatorial Winstress curl. We do see also the smaller scale structures which are associated to the orography, to the difference orography, which is not seen. This is the Winstress curl, but reconstructed from the numerical model. Numerical model obviously does not reconstruct these fine scale structures because they doesn't have enough resolution of the Earth orography. and therefore doesn't see the mountains. Not seeing the mountains doesn't see the Winstress Curl either. While in satellite, it sees everything. Okay. And here is the Winstress Curl, which appears here more, which appears also here, suggests another major current suggests that the impact of strong SST fronts on the wind is important, because if you have the thermal front, the strong changes of temperature, sea surface temperature, this also changes the stability of the air over the sea and changes also the wind field. So it's not only the orography which influences, which impacts which impacts the wind field, but there is also the temperature, the thermal conditions over the world ocean. I zoomed a little bit here, and you can see that in the satellite images, you can see that there is the Winstress Curl positive, following simply the Gulf Stream. Why the Gulf Stream? Because the Gulf Stream is bringing the warm water from the equatorial areas toward the polar areas. Therefore, there's a strong differences in temperature between the pathway of the Gulf Stream and the rest of the Atlantic Ocean. And consequently, the wind stress feels, or the wind velocity feels these differences in temperature, and then this reflects also to the Winstress Curl. Okay, here is simply the wind-driven circulation only associated to the open ocean effects, and this is the annual mean. This is the Winstress Curl, but associated only to open ocean effects. You can see that there is no signs of the influence of the Gulf Stream, and here is the similar to what we have seen before, and this is the wind-driven wind stress, and Winstress Curl related to let me see. Winstress Curl related to Eggman transport convergence and divergence. So here is the we assigned the areas where there is the upwelling or downwelling, which are consequences of the structure of the wind field. You can see the Eggman downwelling and Eggman upwelling, and how it looks like related to Eggman transport convergence or divergence. This is one interesting thing, is that what is also important to mention is the surface nitrate distribution. You remember I mentioned in one of my previous lectures, I mentioned that if we have upwelling, we have, and also I mentioned today, in an upwelling, the colder water from deeper layers, it reaches the surface, and you can see the signs of upwelling from the lower temperature. This is one aspect of the upwelling. But the other aspect of upwelling is that by bringing into the surface area, bringing the deeper layer water, you bring nutrients. Why you bring the nutrients? Yeah, I already mentioned this when we were talking about the dense water formation. The deeper water is rich in nutrients. Why is it rich in nutrients? Because all the phytoplankton which consumes the nutrients lives in the first 100-meter depth. Therefore, the first 100-meter depth of the ocean is very poor in nutrients, because this is a nutrient poor layer, because the phytoplankton lives there, and therefore it eats them, it consumes them. If we have the upwelling, then we bring the nutrient-rich water into the surface layer. So the upwelling areas can be recognized not only from the temperature lower than the surrounding waters, but also from the presence of the higher concentration of nutrients. If you remember, the downwelling areas are in the subtropical gyres here and here. These subtropical gyres are downwelling areas. Therefore, there is the pumping of the surface water into the deeper layers, which then has as a consequence the lower concentration of nutrients in the surface layer. Vice versa, if we have upwelling areas, which are associated to the mid-latitude gyres and to the Antarctic circumpolar waters, then you have the strong concentration of nutrients. Okay, so there are two indicators of the upwelling. One is the temperature, the lower temperature than the surrounding water, and the other one is high nutrient concentration, higher than the surrounding waters. So you see that this is the equatorial areas which has the higher concentration of nutrients. Why there? Because there we have the equatorial upwelling. So equatorial upwelling is obviously has the same phenomena as the Antarctic circumpolar current, as also this mid-latitude cyclonic gyres, has a higher concentration of nutrients, the same as you would see from the horizontal temperature distribution. So this is one of the indication of the nutrient-rich, or the presence of nutrient-rich waters from below the euphotic zone. Euphotic zone is the zone where euphotic zone is the area, the layer where the light reaches, where the light enters into the water column, where the phytoplankton or chlorophyll-rich plants can live. So now let's see let's now try to address the wind-driven circulation from the point of view of this east-west asymmetry, because since we have trades in the subtropical areas, we have a westerlies in mid-latitude areas. So this is the result of this is the formation of this large subtropical anticyclonic gyre in the ocean. But the experimental data shows that it's not like that. That it's not symmetrical between east and west. That the western part is the currents are more intensified than the eastern current. You can see this is it has this subtropical gyre with this asymmetry, east-west asymmetry. Therefore, this image, what you can see on the left-hand side, is not really something which reflects the reality. In reality, we observe this on the right-hand side. We observe the westward current near the equator, the eastward current near the mid-latitude, but there is this strong asymmetry between east and west. In west, there are strong northward current, and along the east coast, there is a relatively weak and weak southward current. So here we have the something what we already mentioned is the conservation of potential vorticity. We have the planetary and stretching, and here is this. This is important term. This important term says what says it says that if the water particle is moving from one latitude to another, it changes this beta is this is the df/dx. This is the changes of the Coriolis parameter with latitude. So if you have the movement of the water column from north to the south and vice versa, you end up with having the vertical gradient of the vertical velocity. Okay, so this is the meridional transport beta v, which is the product between the beta effect. Beta is the derivative of the Coriolis parameter in a zonal direction is proportional to the vertical Eggman velocity, which is this thing what we mentioned here. If we move the water column from latitude theta1 to latitude theta2, but due to the changes of the f of the Coriolis parameter, the potential vorticity has to change. So there should be the vertical velocity, which will change the relative vorticity of the water column. Okay. So this is due to the conservation of potential vorticity, so this thing says simply that. So between the maximum westerlies and maximum trades in the subtropics, there is Eggman downwelling and therefore equatorward flow. Okay, so here you have the Eggman downwelling, here which is this here, and you have the equatorward flow. So you have the equatorward flow in this part here on the western boundaries. On the eastern boundary is the opposite. So let's see how it looks like in the vertical cross section. These are the currents in the vertical cross section across the subtropical gyre. That's the current. You have the western intensification, the strong current along the west coast, and the relatively weak southward flow along the east coast. What is happening is that I'll show you this thing here. Let me show if I have here. Sorry, I have to find it. There is a nice no, sorry, I'll try to find it. Just a minute. If you have a little bit of this is just to figure out. I get this. I think it's just okay. Eggman pumping, no. I have a very nice it's not here. I have a nice illustration of this. Oh, here it is. Can you see it now? Can you see this one? No. No. Okay. So I have to stop sharing, and I have to reshare. Reshare, condividi. Here it is. Now you see it? Huh? Yeah, good. So now we know how to do it. So this is the situation which is really not true, which is we don't find it in the ocean. This is what we find in the ocean. How do we explain this? Let's first look at this explanation and see how we can explain this symmetry. The wind, as you can see from here, the wind impacts the negative vorticity into the ocean. So here is the negative vorticity input from here. And due to this thing here, the relative vorticity, due to the input of relative vorticity, which is negative, the water particle has to move southward. So it moves southward, gaining it moves southward, and so you have these changes of it goes to gains to the positive vorticity. When the particle goes toward the west coast, if it goes northward, since the wind is inputting the negative vorticity into the water column, the particle cannot move northward, because in that case, this is against the potential vorticity conservation. Because if you input the negative vorticity into the water particle, it should go southward, because you are squeezing the water column, and you are increasing the theta, and then you have to decrease also the F. Here at the left-hand side, at the western part, again the wind is impacting the negative vorticity, but the particle has to move northward, because this is the return flow. But it cannot move northward, because it would move, that means it would move into the higher planetary vorticity area. Therefore, somehow this negative vorticity input has to be compensated by the shear, by the horizontal changes of by the horizontal changes of the current speed. And this is this thing here. Here is the strong changes of the shear, strong changes, positive shear, positive relative vorticity, which then, if you end to this thing, it will compensate for this, and then particle can go northward. So the particle or the water masses are moving northward here only if the horizontal distribution of the velocity is such that on the left-hand side you have a relatively weak flow, and very, very quickly increases moving away from the coast. So this is the coast, okay? So quickly moving from the coast, very quickly, the current increases, and you have the very strong positive shear. And this positive shear then compensates for the negative, for the input of negative vorticity from the wind field. And this is the only way, the only mechanism which enables the water to move northward along the western boundary. And this is why, due to the potential vorticity conservation law, this east-west symmetry is present. And this situation is not possible, since all over this area the wind impacts the negative vorticity, and so this is compensated by the relative vorticity of the water column. How do we get this relative vorticity along the western coast? Along the western coast, we get this type of vorticity in the way that the current is zero at the coast, and as you move from the coast, it increases very fastly. So the only way you get this positive vorticity along the western coast is by having the friction. So the friction really blocks the current at the coast, and then as you move from the coast, the current increases. So this is implicitly from here you can see that there is not only friction at the surface and at the bottom, but there is also the lateral friction. In all these cases, the friction enables the water to start from a certain velocity, which is similar or equal zero to the interface, and then increases very quickly within this layer. Exactly what is happening in the surface Eggman layer, in the vertical Eggman layer, where the water velocity is very strong at the surface and decreases exponentially. Here you get the same thing. You get the you get the horizontal boundary layer where the current is zero at the surface, because zero at the coast, because the coast doesn't move, so the zero is the current is zero at the coast, and then increases very fastly toward the open sea. And this is what creates the horizontal shear, which compensates for the wind input on the velocity. I can see that I really cannot see, but I imagine that you have some problems with understanding that. But you may want to ask me the questions. I will be happy to respond whenever you want. So now let's go back to the the previous PowerPoint. Let's see. Okay, what is this? Oh, that's Verdup, I think. Can you see it now? Swedish Transport in Pacific. Okay. So and this balance, what we have now, we have just discussed a little bit. This thing is called the Swedish Transport. The transport due to the input of the Eggman pumping or suction into the water column, and compensative transport northward or southward in order to compensate for these differences. And this is how the Eggman transport drive the underlying circulation by potential vorticity conservation and the let me see. Okay. So this is that's. Oops, sorry. So so this is we are able also to calculate the Eggman pumping, Eggman pumping is from the equations we already seen before. We are able to calculate the Eggman pumping from the curl of the wind stress. So the curl of the wind stress gives you the Eggman pumping, and so that's how the Eggman pumping looks like, calculated from the wind curl of the open ocean. And so the Eggman pumping, for example, bluish areas are the downwelling areas where the Eggman pumping is from the surface to the deeper layers, or and then you have the yellowish red area is the Eggman suction to, that means the water blowing going upward. And then you have in a function of that, you have the equatorward or poleward sweater transport. The Eggman pumping, which means that there is the water vertical velocity is downward. There is the equatorward sweater transport because due to the potential vorticity conservation, you're increasing the vorticity of the water column, but in that case, zeta plus F has to be 0, so your water particle has to move southward. So this is the sweater transport which goes southward. Yellowish area means Eggman suction, so that means the suction of the water into the surface layer, and then you have the squeezing of the water column, which means that the water has to move northward in the area where the F, the Coriolis parameter, is larger in order to keep zeta plus F, the relative vorticity plus Coriolis by absolute vorticity, by planetary vorticity has to be constant. So in the area of Eggman suction, the water has to move northward or poleward, to say better. And obviously, then we can calculate the total meridional north-south transport across a certain latitude, and integrate the sweater velocities along that latitude. And for example, here, this thing, if you integrate from here to here, obviously from east to west, this has to be 0. Whatever is going northward has to go southward in a first approximation. And if you do the integral over time enough long, why do you have to have the integral over long time over a long period of time? You have to do the integration of enough long period of time in order to make sure that the Eggman solution is valid. And we know, and we have seen while analyzing the Eggman solution, we noticed and we've seen that the Eggman solution is valid for the very long time scales, for the time scales on the order of months. Therefore, if we do this integration of total meridional transfer from here to there, the longer is the period of integration, the closer we are to the sweater transport, or the closer we are to the 0 Eggman transport from here to there. You have always to remember that if you go and it's any certain place in this area here, and you do your measurements and compare this with the Eggman's sweater transport solution, your measurements will not be identical to what is obtained from the Eggman solution. Why? Because we are not measuring only when we are measuring, we don't measure really only the Eggman's the wind influence, the current influence by the wind. We measure the whole spectrum of currents which are passing through that specific area. So that means we are measuring the wind generated current, we measure the tidal current, we measure the thermohaline circulation. Obviously, it's rather simple to eliminate the tidal currents because you do the long-term average, and then you eliminate the currents. But then you cannot distinguish between, for example, between the thermohaline circulation, so the circulation which is dependent on the gradient of temperature and salinity, and wind-induced sweater like a transport north-south. Therefore, you always have to be careful while measuring something in the ocean to make sure that what are you measuring? You have to know what are you measuring. You have to know all the physics which stays behind all these measurements, what you do, and behind all these processes and all these phenomena what you are studying. Otherwise, you will not be able to interpret this, because our purpose of measurements in the ocean is to try to interpret whatever is happening in terms of the knowledge, in terms of the physics in the ocean. Therefore, knowing the physics and knowing the characteristics of the measurements, the accuracy and precision, how long do you measure, where do you measure, in which depth, at which depth, and so forth. Only in that way you are able to interpret these measurements, and this is the final scope, final aim of the measurements, is to try to interpret this of the present knowledge on the physical mechanisms and processes in the ocean. And this is the Swedish Transport. And so this is obtained from the annual mean wind stress curve. Swedish Transport, as we said, the Swedish Transport is obtained from the mean stress curve. And you can see that it reflects what is happening in the Winstress Curl. Obviously, you have these bluish and yellowish areas which are coinciding with the subtropical and mid-latitude gyres. You can see also that in the equatorial areas there is a blank. It's blank because the Swedish Transport is not defined, because the Coriolis parameters approaches to 0. And so this is the Swedish Transport, wind-driven and equal, obviously transport of the wind-driven Swedish gyre equals the predicted transport of the return flow in the western boundary current. The same thing is the Swedish Transport in the Pacific. It was in over the World Ocean. In the Pacific, again, you have here this is what we already discussed before. Western boundary current is one of the example is the Gulf Stream, which is very, very highly studied. You remember when I showed you at one of the very beginning of the course that there was a huge experimental efforts in this area here. So the Gulf Stream is pretty well studied. There is also there are also measurements of the meridional transport, direct measurements of the meridional transport, which consist of a series of current measurements along the 25 degrees north here, which gives us the idea how and what is the possible, or if there is any changes in the meridional transport. You will see later when we will be talking about the climate change. You will be seeing that how important is the meridional transport, meridional heat transport in determining the climate. One of the first observation of the Gulf Stream was in a 19th century, because a lot of ships were navigating, so they noticed the presence of the strong current here. Here the currents are on the order of 10 centimeters per second, but suddenly you enter into the area where the current is 1.5 meter per second in the surface. Therefore, you can easily, by navigating through this area, you can see these changes on the velocity. And in fact, the first measurement of the Gulf Stream was obtained from the ship drift in that area. So by looking at the drift of the ship in that area, the people were recording the currents. Okay. Here is all the explanation why it's only western boundary. This is what we mentioned before. This is the western boundary current. This is the southward interior flow, weak, sluggish flow on the interior of the basin. This is the Sverdrup flow due to the input of the vorticity into the water column. And this is really the return flow, because you cannot have that all the flow goes southward and there is no return flow someplace. There should be the compensative northward flow along the ocean, across the ocean, across the meridional flow. And this is what I was talking to you before. This is the western boundary current, which is really a return flow for these Sverdrup southward interior flow, which is very weak current flowing southward due to the related to the potential vorticity conservation law, and which makes the water column moving southward. The return flow, which is really a compensation flow, is along the western boundary, which is possible only along the western boundary, because there the frictional boundary layer enables the positive relative vorticity, which then enables the water particle to go southward, to go northward, and still the potential vorticity is conserved. And okay, this is that's this thing. This is the western boundary. And let's see what is the amount of water which is transported by these currents. This is the huge amount of water which is transported with these currents. You can see here that in the Gulf of Mexico, the total amount of water, which is the rate of water transport, is 31 Sverdrup. Sverdrup means million meter cubic per second. So at the very beginning, where the current starts, the Gulf Stream starts, we have like a 30 million meter cubic per second of the water transport. The more we go toward north, it increases. This amount of water transport increases. So already at the Cape Hatteras, we have around 60 million meter cubic per second. So this is a huge amount of water, and this is a huge amount of heat and salt which is transported northward. And if you go further northeast toward the coast, because at a certain moment the Gulf Stream detaches from the American continent and goes toward Europe. We will see later on why these, how this influences on the climate, and it reaches 150 millimeter cubic per second. This is a huge, huge amount of water which is transported with this current, which is the compensation, of the current which goes southward in all this interior of the ocean due to the input of the negative vorticity from the wind. So 150 Sverder more or less, or between 60 and 150 Sverder moving northward, and the return flow is more or less like that. And so here I won't go into more details about this thing, and I would prefer now to stop, and we will be going on next week. Next week we will be having the discussion on some influences of the changes of the vorticity in the world ocean, and we will have some time also to for illustration to show you some solutions of the equations of motion, where vorticity represents represents the force which causes the movement, not only the steady movement as it is the case of the Eggman solution, but also causes some wave solutions, which we will be just mentioning very little, and then you will be having more details about that in next lectures by two other speakers. So have a good weekend, take care, and we'll be seeing on Monday at the same time at the same place. Ciao.
Ciao. Thank you.
Ciao.
Thank you.
Ciao.
Have a nice weekend.